Hey everyone, in this video, I'm going to talk about the Poincare Bendixson theorem. So Poincare theorem is essentially telling us all the possible dynamic you can see in the 2D in two-dimensional phase space. So these are all the possible dynamics you'll see: fixed point, periodic orbit, and this orbit. And the core idea of this the Poincare theorem is saying that the trajectory, they cannot cross each other for a time-independent Hamiltonian. Okay, so this is a very mathematical theorem, and by just looking at the words here, you probably don't have a very nice intuition at the moment. Instead of going through all the mathematical proof for this theorem, what I'm gonna do in this video is to give you a physical explanation and intuition about how to see this theorem naturally from a physics perspective. So let's take a look at this simple pendulum problem. This is the Hamiltonian. Here we have the Hamiltonian for this pendulum problem. And because this Hamiltonian has no time dependent, so the Hamiltonian will be a conserved quantity. So this is exactly the case where we can use the Poincare theorem. Okay, so great. And we also happens in this Hamiltonian, the Hamiltonian is also the total energy. So we can use total energy to think about Hamiltonian in this case. Okay, so that will also give us a lot of intuition. All right, so let's go ahead and try to plot out this trajectory for this Hamiltonian. So because Hamiltonian is a conserved quantity, so let's try to scan throughout this Hamiltonian, or you can measure total energy from small energy to large energy. So say when the energy is very small, then you can imagine the P phi will be very small, and the angle will be very small. I'm going to ignore all the constant here because it's not going to affect the shape of the trajectory. So I'm just gonna say these are all either 1 or 1/2, and so that's my Hamiltonian. Because phi is so small, so I can actually do a small angle approximation here, replace that, and get P phi squared plus phi squared to be Hamiltonian. So this is a very small number again. And this equation is going to give me a circle. If you keep all the constant here, you may get ellipse. But no matter what you're going to get is will be a very smooth and closed shape. So that circle is saying if I release a pendulum from a small angle, this pendulum will swing this way. So that's clockwise. So it's negative P phi. So that being said, if my particle is released from this point where I have a little bit phase and no angular momentum, and when I release it from here, then this particle will then next flow this way. So the angle will decrease, and the momentum will also increase, but in the negative direction. So this particle will flow from this trajectory to here. And then it will keep moving, swing all the way to the left, and that will be this point. And once it reach this point, it will swing back and do a counterclockwise direction. So that will be positive momentum. Okay. So essentially, if my initial condition is releasing the ball at this point, then it will just swing back and forth, just like looping this circle. Okay, so that's what happened at small energy. If my energy is slightly increased, you can imagine that phi, I cannot do this small angle approximation anymore. But you can imagine the trajectory will still be somewhat oscillating. It's just not simple harmonic oscillation. Okay. It will be oscillating non-linearly. Okay, but the phase flow is still going in this direction. Okay, so now let's take a look at, let's now look at extremely large energy. Okay, so say I release my particle here and there was a huge energy. I'm pushing it so hard. Now what's gonna happen is this guy, because I'm pushing it so hard, so it will just like boom, like it will just go this way. It will just keep making the whole circle around my anchor point. And throughout this process, all of my momentum will be negative. So if I try to find out if I try to, make the plot on my phase space by using decimals or any graphing, I will see this shape. Okay, so let me plot it out. It will be this green shape. Okay, so specifically this one is saying I'm going this way, right? So meaning I am starting from some phase and then it's going to have a negative momentum. So it will be this. But with the same energy, I can push this guy not to the left. I can push it to the right and make it a counterclockwise direction. So the phi will increase as the time goes, right? If it's going to the right, you'll see this phi will increase in the looping in another direction. So in that case, say this is my phi, and as the time increases, it will just keep going to the larger and larger phi. So if I trace back in time, then this whole phase flow will look like this. All right, so now let's come back and take a look at the Poincare theorem. So the core idea about Poincare theorem is the trajectory they cannot cross each other. And this makes a lot of sense because if you think about it, the way we plot out all this trajectory is we will assume a specific energy, right? So say when energy is very small, is 1, I plot out this circle. And when energy is 2, I will plot out another circle, right? And for my state, and because the energy is conserved, right? So when my state evolve as the time goes, the energy will be a constant. So this guy has no choice but to staying at the same trajectory. And the energy and the particle with higher energy will stay in its trajectory. These two trajectory can never cross like this. Because if it cross like this, then the particle will be very confused. So as my particle travel over, then the energy will be 2 joules. But then at the intersection point, this particle or this state will feel the energy of 2 and the energy of 1 together. And that is very weird because if this particle now jump to another loop because it is continuous, right? So if it jump to another loop, then essentially this particle is losing energy at this point. And that's not allowed in our Hamiltonian because its energy should be conserved. So that's why it's impossible to have a state that has two different energy at the same time. So different trajectory, they cannot cross each other. So all this oscillation closed orbit, they will never cross each other. And same for the closed orbit on the top, right? This one and another one with higher energy, they will never cross. So this just makes sense because energy has to conserve. One particle cannot have two energy at the same time. All right, but there is an exception. So that exception is happening at the critical point. As we tune our energy from small to large, we can see that the trajectory for that energy will go from one trajectory to two trajectories. So there will be a sweet spot. There's a critical point where 1 becomes 2. And that's the yellow line here. So you can see the yellow line it's kind of like the hybrid of one trajectory because it's kind of a closed loop. But you can also think about that it's two trajectory where this is one of them and that's two of them. But because now they touch, so it seems like a closed loop if you just look at the middle. Okay, so this is the critical point. And in this critical point, this guy and this guy is, we call them fixed point. In this two fixed point, you see this trajectory and this trajectory, they kind of cross each other, but that is fine because they share the same energy. So going from one trajectory to another trajectory, that doesn't violate the energy conservation. So this is fine. Okay. And so these two are the fixed point, and the line that connecting this fixed point, these two fixed points are actually the same fixed point because they correspond to the same spot. So let me show you here. Okay. So when phi is pi, meaning this ball will be on the top here. And when the phi equals negative pi, it also means the ball on the top. Okay. So these 2 points are actually the same point. Okay. So the line connecting between them, like this line, is we call the homoclinical orbit. Okay, which is this one. And those two little points are the fixed point. Okay. So how do we understand? How can we understand this picture? So let's try to start from a fixed point. So let's say I'm trying to start from the fixed point at the left. So the fixed point at left is saying, the ball is on the top at negative pi phase, and then it's not moving. So this is a unstable equilibrium point. The ball at this moment, because it has no velocity at all, so it can swing to the left or swing to the right. If it swings to the left, then, well, the phase will be increasing because it's less and less negative, and then it will be counterclockwise, so it's positive in momentum. So essentially, you are feeling this going this way. Okay. So when this going down and then swing up, then it will reach to the fixed point again. So essentially come back to itself. Now when it come back to itself, again, it's not moving at all. So now this guy can choose to go to the left or go to the right. It makes no difference to this guy at this moment. So if this guy goes to the left, then it will go up. If this guy chooses to go to the right at that moment, the phase will be decreasing, and then it will be negative momentum, so it will flow back. So no matter which way they choose, they will keep flowing until they reach the fixed point again. Then they need to make a decision. They either keep flowing clockwise, or they can keep flowing counterclockwise. Okay, so let me just trace the time and then finish all the flow. It will look like this. Okay. So that's why this is a fixed point. Because no matter I'm going left or I'm going right, the energy will be the same. So I can choose either way. So two of my trajectory, they can intersect at the fixed point. So here you can see that there's a one trajectory going this way, and then another trajectory going this way. And these two trajectory, they actually touch each they will touch. And this is okay because both of the trajectory, they share the same energy. So I'm not violating energy conservation anyway. So this is fine. So that's why the trajectory, they can cross at the fixed point. Yeah. And you may wonder, when will this fixed point happen? This happens when Q dot and P dot are both 0. So Q dot and P dot both 0, meaning this guy is not moving and it's also not accelerating. So it's totally still. And because it's totally still, so going to the left or going to the right, like choosing trajectory makes no difference to this guy. It can always choose what it likes. So the fixed point usually happen at this point. There's one more fixed point in this phase diagram, which is this point. That's when phase and momentum, they're both 0. And so, yeah, so it's just a fixed point because it's not moving at all. So there are 3 fixed points here. Two actually, like one at the top and one in the middle. The one in the middle is a stable fixed point. The one on the top is unstable fixed point. So the particle, when it comes to this point, it can flow out, right? As the picture shows, it can flow out like this. Okay. So now we have completed our phase diagram for this problem. Okay. So now let's go back and review our Poincare theorem. So Poincare theorem is saying trajectory they cannot cross for a time-independent Hamiltonian. So this now makes sense, right? Because time-independent Hamiltonian energy is conserved. Because the energy is conserved, so a state, if the trajectory they cross, then meaning the state at the intersection will have two energies, and that's not allowed because the energy is conserved. All right. But trajectory of the same energy can actually cross each other at the fixed point. Fixed point is the point where Q dot and P dot are both 0, meaning the particle is not moving at all. And because the particle is not moving, so when my state flow into this fixed point, its memory will be reset because it's not moving at all, right? So now its memory will be reset. It can still continue on its trajectory, or it will move on to another trajectory. It can jump between two trajectories. Yeah. So that's why the trajectory they can cross at the fixed point. And these are all the possible, and because of that, they cannot cross. So these are all the possible orbit you will see. Fixed point, periodic orbit, the homoclinic orbit, which is what we see here. Heteroclinic orbit, meaning if I have two different fixed point in the space, and then there could be a flow going from one fixed point to another fixed point, and that will be heteroclinic orbit. Okay, so yeah, I hope this example will give you, more intuition now about why this theorem will be true.